The process that powers the sun and the stars is called fusion. It is energy that makes all life on Earth possible. This fusion energy is produced in the sun by fusing the lightest atoms, such as hydrogen, together at extremely high pressures and temperatures. At these temperatures, gas becomes plasma, the fourth state of matter. Solid, liquid, and gas being the other three. Telescopes such as the VLA and ALMA and space-based observatories such as NASA's Hubble and Kepler have captured stellar visuals of the Sun and galaxies millions of light years away. However, as impressive as these images are, scientists wanted to create the events that might have led to the creation of these planets and stars to strengthen their understanding of the cosmos. In addition, researchers in plasma physics are trying to build fusion reactors of their own to create fusion energy as a safe, economical, and environmentally attractive source for the world's long-term energy requirements. On opposite ends of the United States, there are facilities working on fusion research: the National Ignition Facility in California and the Princeton Plasma Physics Laboratory in New Jersey. But first, what is fusion? Fusion is what happens when the nuclei of light atoms overcome the electrical resistance that keeps them apart and get close enough to activate the strong nuclear force that holds them together, or fuse. When fused, they form a bigger nucleus. Two elements combine to create a different element at the level of the nucleus. Making elements fuse requires an enormous amount of heat and pressure, like that found in the cores of the Sun and stars. Before it formed some 5 billion years ago, the Sun was a cloud of gas, mostly made up of hydrogen and helium. Eventually, the cloud became so massive that gravity caused it to collapse in on itself, and it formed a star. Numerous collisions in the core of the Sun freed electrons from ions, forming a plasma state. Fusion began in the Sun when collisions between ions became so frequent that the ions got close enough to fuse together. Thus, the Sun is a natural fusion reactor.
The Princeton Plasma Physics Lab is a Department of Energy national laboratory. We are trying to confine a plasma 10 times hotter than the core of the Sun, and at that temperature will generate fusion energy that we will then convert to electricity. We're trying to produce a star here on Earth.
So a plasma is a hot gas. This beautiful, distinct state of matter can be manipulated by, let's say, a magnetic field. And there are examples all around us. It's the Sun and the stars and 99% of the visible universe.
So fusion energy is the way the Sun works. It takes very light elements and fuses them together to make heavier elements. That releases energy. It's the opposite of fission, where you take very heavy atoms like uranium and split them apart.
Scientists at the Princeton Plasma Physics Laboratory, or the PPPL, involved in the National Spherical Torus Experiment, or NSTX, use a spherically shaped magnetic device to study the effects of fusion. A tokamak is a device that uses a magnetic field to confine plasma in the shape of a torus. A stable plasma equilibrium requires magnetic field lines that move around the torus in a helical shape. NSTX uses deuterium, one of two stable isotopes of hydrogen, to produce a plasma that is shaped like a sphere with a hole through its center. The unique plasma configuration has the ability to confine a higher plasma pressure for a given magnetic field strength. Magnetic fields confine the hot plasma since solid materials cannot withstand the extremely high temperature of the plasma. The tokamak uses a combination of external magnets and a current driven in the plasma to create a stable confinement system. Because the amount of fusion power produced is proportional to the square of the plasma pressure, scientists propose that the use of spherically shaped plasmas might allow the development of smaller, more economical fusion reactors. On the West Coast, the National Ignition Facility, or the NIF, uses 192 laser beams that converge on a target to produce temperatures, pressures, and densities that are similar to those in the cores of stars, supernovae, and giant planets. These experiments are particularly relevant to astrophysics, the branch of astronomy focused on understanding the physics of the universe. The physics of stars and other astrophysical phenomena such as supernovae, black holes, and planetary interiors are not well understood. By creating tiny parcels of plasmas under extreme conditions, scientists at the National Ignition Facility can better understand the physical processes that they could only previously observe from great distances. In essence, the NIF allows scientists to visit inaccessible parts of the universe. Experiments at the NIF are transforming astronomy from an observational to an experimental science. What is ignition? NIF ignition experiments use a very small container called a hohlraum that holds a plastic capsule filled with deuterium and tritium, which acts as fuel. Deuterium is extracted from seawater, and tritium is produced by the transmutation of lithium, a common element in the Earth's crust and oceans. To create fusion reactions, scientists simultaneously direct 192 lasers into the small hohlraum with a peak power of 500 trillion watts, roughly the energy the United States consumes every 6 minutes. This heats up a 1 centimeter gold cylinder to millions of degrees, which produces X-rays that are directed at a point the size of a BB pellet. The X-rays blast the shell, creating an implosion that shrinks the gas inside the pellet to 1/35 of its size, compressing the deuterium and tritium to incredible densities. At the center of this hydrogen plasma, in an area smaller than the width of a human hair, the atoms fuse. This gives off energy, which should in theory set off a chain reaction that ignites the rest of the hydrogen and creates a self-sustaining ball of fusion. The National Ignition Facility made history on July 5, 2012, when its 192 beams delivered more than 500 trillion watts of peak power and nearly 2 megajoules of ultraviolet laser light to its target. That's 1,000 times more power than the United States uses at any instant in time, and nearly 100 times more than any other laser facility regularly produces. But they have a long way to go in making it a reliable, constant source of energy.
I was attracted to plasma physics because I wanted to help turn fusion energy into a reality. I liked the idea of being part of a larger mission, with the whole global community working together to solve this grand challenge. I've had a wonderful experience here at PPPL. I've had the freedom to explore the problems that really interested me. And not only that, but I've been able to travel all over the world and meet with other scientists and collaborate with them in solving these problems.
While it can be extremely difficult to achieve, a career in these fields can be challenging and highly rewarding. From engineer to nuclear physicist, you could help shape the future of the world's energy production. A fusion power plant would not emit greenhouse gases and would not require disposal of radioactive waste. A fusion power plant could run off an almost unlimited fuel supply and would present no danger of a meltdown. Since nuclear fusion offers the potential for nearly unlimited, safe, and environmentally friendly energy, the U.S. Department of Energy has made fusion a focal point in the nation's long-term energy plans, with investments into magnetic fusion energy and support of the NIF. And hopefully, fusion will soon play a role in our ever-growing energy demands.